So we've seen some quadratic complexity sorting algorithms. Okay, but not great. And clearly we'd like to get the sort as efficient as possible. And fortunately, we already know an idea that we can use to do that, and that's to use divide and conquer. If I could somehow break the problem down into half-sized chunks and do work on that, that would be really great. And that leads to a great technique called merge sort, a very common sorting algorithm. And here's the basic idea of merge sort. If I got a list of length 0 or length 1, it's already sorted. I'm done. If I have a list longer than that, let's just split the list into two parts of roughly equal size and sort each of them. Once I've got them sorted, I'm going to merge them together. And I'm going to do that, as we'll see in an example in a second, by taking advantage of the fact that if I have two sorted lists, I can just look at the first element of each, ask which one is smaller, and put it into the result, and then look at the next portion of it. That's going to be a nice linear time solution. And so when I do that, once I've got to an empty one of those two lists, I just copy the rest of the list, and I'm done. You can see the idea. Break it down into smaller and smaller size problems until I get to something that's trivially sorted. And then I'm going to merge those results and keep merging those results out, taking advantage of the fact I'm splitting the problem in half at each stage. Let's look at a visualization of that to get a sense of that. Again, it's a nice divide and conquer idea. So if I've got a big list that's unsorted, I'm going to split it into half. If those are still too big and they're unsorted, I'll keep splitting until I get down to something where I've just got lists of one element. Once I'm down at that level, merging is actually really easy. I just look at the two and decide which one's smaller, and that gives me lists of size 2 that are sorted. But now merging those is also pretty easy, as we'll see in a second, because I simply look at each of the elements in the two lists, putting the smallest one in, and I merge those, and then I merge those, and then I merge those till I get back to something that is overall sorted. Nice divide and conquer algorithm. Should have a nice complexity. We're going to look at that in a second. Before we do, let's again get Professor Guttag and a set of MIT students to give you a little visual demonstration of doing merge sort. And then we'll come back and look at what's the actual complexity of the algorithm.
So we're about to demonstrate merge sort, and we're going to sort this rather motley collection of MIT students by height. So the first thing we need to do is we're going to ask everyone to split into a group of 2. So you split a little bit. You 2 are together. You 2 are together. You 2 are together. You 2 are together, and you are all by yourself. I'm sorry. All right. So now, let's take the first group, take a step down, and what we do is we sort this group by height with the shortest on the left, and look at this, we don't have to do anything. Thank you. Feel free to go back up. We then sort the next pair, please, and it looks to me like we need to switch. All right, take a step back. Ladies. Okay. Ladies, gentlemen. Also okay. And again, okay. And I think you're in the correct order. Now what we do is we take these groups and merge the groups. So let's have these two, going to sort these groups, have them step forward. And now what we're doing is we're doing a merge of the two sorted groups. So we start by merging them. We'll take the leftmost person in this group and compare her to the first person in this group and decide she's still the shortest. Take a step back. Now, we're going to look at you and say, you're actually taller than this fellow. So you now step up there. And we're good here. Both of you take a step back. Now we'll take these two groups and follow the same procedure. We'll merge them. Let's see, we'll compare you, the first person in this group, to the first person in this group. Now it's a little tricky. So let's see the two of you compare. Let's see, back to back. we have a winner. Step back. And now we need to compare the shortest person in this group to the shortest person in this group. We have a winner. It's you. I'm sorry. And now we're okay. Please step back. Now we'll have these two groups come forward. We'll compare the shortest person in this group to the shortest person in that group. I actually need you guys to get back to back here. You are the winner. And it's pretty clear that the shortest person in this group is shorter than the shortest person in that group. So you go there and you step back. And now we repeat the same process. And you can see that we have a group of students sorted in order by height.
So again, that visualization is, as we just saw with the students, pretty straightforward. I'm going to do sub-pieces and sort them and then merge them. And as you see with this algorithm, or the visualization of this algorithm, it starts with smaller pieces, does a merge sort on those smaller pieces, and keeps doing that until it can do a merge sort on the entire element. And you can also see, even if I get to two sublists of half the size of the problem, the merge is pretty straightforward to do. And that's what's going to give us the power of having a nice complexity to this algorithm. So let's look at the merging part, and then we'll look at the subdivision part. The idea here is if I've got two lists that are sorted, I want to simply say, look at the first element in each, that comparison, and put it into the result. The smallest one goes in. Having done that, one of the lists is now smaller. And again, I'm going to look at the first element of each. In this case, the 2 is going to go into the result. And the second list has gotten smaller. And I'll simply keep doing that simple comparison of the first element of each list, putting the smaller one into my result, until I get to a stage where one of the lists is empty. In which case, I simply copy the remainder of the list that's not empty to the end of the list, and I'm done. You can see I might have to take a linear number of steps in the size of the list to be able to get to that stage. But that's still not bad. And that's going to be nice because in many cases it will actually be faster if I actually don't have to look at all the remaining elements of a list. So merging is going to be pretty straightforward. So here's the code that would do it. Right. Merging simply says, given a left and right sublists that we know are sorted, what am I going to do? I'm going to set up a result into which I'm going to store the values. And I'm going to set up a couple of indices, I and j. And basically, I'm going to let them walk down the list. So again, I'm not making copies of the list. I'm simply looking at the elements. As long as I is not to the end of the length of the left sublist and j is not to the end of the length of the right sublist, I'm going to do the comparison. And if the left one's smaller, I'm going to add that element into the result. Again, I know append is constant, so that's nice. And I change I, just as I did in my example. I now move my index in the left list up by 1. On the other hand, if the right element is smaller, I add it in and I change j. And I'll keep doing that until one of the lists is exhausted. And then these two cases simply tell me, in either of those cases, just add in the remainder of that list. Great. What do I know here? I've got left and right sublists that are ordered, so I'm just moving the indices for the sublists. It's avoiding that copy of the list. And so that cost is basically going to be linear in the size of the list. When the right sublist is empty, I copy the rest of the left sublist. When the left sublist is empty, I copy the remaining elements in the right sublist. And then I just return the result. What's the complexity here? I go through two lists, but only one pass. And I'm only comparing the smallest elements in each sublist. So the complexity is basically order of the length of the left and the length of the right sublists. Overall, I've got order length of the longer list comparisons. And so this is always going to be linear in the length of the lists. So the merge stage is linear, depending on how long those lists are. Okay, now how do I put it together? knowing I know how to do merge, I do the following for merge sort. Given a list, I say if there's only 0 or 1 elements there, I'm done. Just return a copy of the list, and I'm all set. Otherwise, there's that nice pattern. Find the midpoint. Break this in half. Find the midpoint by taking the length of the list, doing an integer divide by 2, and then simply do a merge sort on one half of the list. That's the smaller half of the list. Do a merge sort on the larger, I shouldn't say larger, on the left side of the list and the right side of the list. Once I get those back, simply merge them together, and I'm done. So what I'm doing here is treating base case, dividing the problem in half, solving 2 subproblems, and then conquering it with the merge step to bring it back down. Nice, crisp, elegant solution. What else do we want to know here? Well, let's just look at an example of how it would do this and then look at the overall complexity. So imagine I have a list of 8 elements, as you see up here. I'm initially going to break them in half, and I need to go off and do a merge sort of the left half. Again, I break it in half, I need to do a merge sort of the left half, and eventually I get down to actually 2 base cases. The first base case, the solution I can just pass back, simply a list of 1 element, same thing with the second one, and I just am doing that merge. I do the same thing with that gets passed up to the place it wanted to do it. I do the same thing with the right half. Same kind of merge, that gets passed, and now I can merge 4 and 8 and 1 and 6 with that simple little linear search to get out the solution I would like. Halfway there, same thing on the other half. Having passed that back, I can go to the other half and very quickly get it down to a base case, merge those results, get it down to another base case, merge those results. Those 2 get back up and get merged into an ordered list, and now I can simply merge those 2 sublists to get out the overall sorted list I wanted. I show you this diagram because you can see that nice pattern. This is breaking it down in a nice way into smaller pieces of things, and you already ought to have a good sense of what's the complexity here. The complexity of the overall breaking down into sub-pieces is going to be probably, and we'll see in a second, logarithmic, because I'm reducing the size of the problem in half at each point. The wrinkle here is that the merge we saw was linear in the size of the problem. So let's put those 2 pieces together. At the first level of recursion, I've got n over 2 elements in each list, and so I've got order n plus order n, which by that additive law of complexity is still order n in terms of solving that problem. Meaning, once I've got the solution, I've got to do basically linear amount of work to do the merge. At the second level, I've got n over 4 elements in each list, and there are 2 merges there. We saw that in that diagram. So while the size of the problem is smaller, I've got twice as many searches. And if you think about it, I'm still at that entire second level looking at each of the elements probably once. So it's also order n. At each recursion level, the merge step is order n. The size of the list is smaller, but I got more of them. And that basically cancels out. I've got a linear search. The good news is, how many times do I do it? I've already hinted at it. You know the answer. I'm doing a logarithmic number of steps because I'm basically saying, given a size problem of size n, at 1 recursive call it's n over 2, at 2 recursive calls it's n over 4, at k recursive calls it's order n to the k. I'm done when n to the k is of size 1. That's when k is log n. And this is an example of something I promised to you earlier. It's order n log n. It's log linear. So it's not quite as nice as logarithmic. It's not quite as nice as linear, but it's a lot better than quadratic or certainly than exponential. And this is a characteristic of a wide class of problems that are really nice. N log n, log linear. Great solution. So what do I have for sorting? I can be dumb about it and use BOGO search. Good luck. I could use bubble sort. I could use selection sort. They both have a similar property that they are quadratic in size. Timing-wise, selection sort is probably a little bit faster. One of the advantages of selection sort is that I can guarantee that the first I elements are sorted. So in fact, if I want to stop the computation after I get some number of the best elements out, I could do that without having to sort the rest of the list. And that's better than doing bubble sort. But my best option is merge sort. And in fact, while we won't do it here, one can show that n log n is the fastest time in which one can actually do a sort. But having an n log n sort time is nice because if I amortize that cost over searching, I actually have something that's going to work out quite nicely. And so now you've seen search, you've seen sort, and you've seen a wonderful example of an elegant class of complexity, which are those log linear algorithms.